Hi everyone, this is going to be a video about the existence and uniqueness of the solution of ordinary differential equations that is in the standard form and come with the initial values. There is a very general theory, and it is usually introduced in some point of first course in differential equation, but I'd like to take this as an first step toward to understanding these two things, existence and uniqueness. So beginning with this very simple differential equations. So here it is. The y is a function of unknown function of x, and right hand side is only in terms of x. And we have a condition that the function value at c is given by a0. So c and a0 are the constants given, and y is the function that is unknown, and the right hand side, that's the derivative, right hand side is the function of the independent variable x. So for example, this would be an example of function whose derivative is cosine x squared, where the main variable is x squared. So this is the fundamental problem of the integral calculus problem this is introduced. So we are looking at this type of question, looking for a function whose derivative is this one, and think about these two questions, existence and uniqueness. So going back to the general setting again, we're looking at the very simple differential equation whose is this, the y prime is this function f of x. So generally the condition put on this right hand side function is continuous. Here it's a one variable continuous function, and y is unknown function of x. So here's the answer to the existence. Why is there exists a solution to these differential equation with this condition, so-called initial condition, is this function we have created here on the right hand side does satisfy all these conditions. So let's look at the right hand side here. This is called the area function. This is the definite interval, starts from c and ends at x, and we're integrating this ft/dt. So this actually calculates the signed area underneath the curve over between these two x values, and there's a constant a0 in there. So all we have to do is that this is a well-defined function and whose derivative is f of x and its condition yc is a0. Then this is the function that satisfies both conditions. So the reason this function here satisfy this condition, this derivative, because the derivative a0 here constant is 0, being f of x, is exactly the content of fundamental theorem of calculus. This particular shape of area function where the lower limit is constant, there's no x involved inside the integrand, and upper limit is simply x, then you can look at this as a function of x, and its derivative of this very special form of area function is exactly f of x. That's the exact content of the fundamental theorem of calculus. Then it is also the fundamental theorem of calculus that connects this one with the existence of antiderivative. But more theoretically important part of the fundamental theorem of calculus is that part I just explained, and not that we calculate this one in practice using the difference of the values of the antiderivatives. The earlier remark is really explaining the existence part here. Typically in differential equation or other parts of mathematics, when you have to show the uniqueness, the argument usually goes like this. Suppose we have two solutions, y1 and y2, that are possibly different, so that it violates the uniqueness. So if you have two functions that are possibly different at some point value x, you take the difference of these two values, two functions, and call that yx. And think about how this yx has, what kind of derivative property and initial value property it has. First, if you differentiate this left-hand side, this will be just this derivative minus the derivative of this one, but both are solutions of this differential equation. Therefore, they have a same value function f of x here, f of x there, so the difference will be the zero constant function. And if you look at this initial condition, at this value c, this y1 and y2 takes the same value a0, because it's a solution to this equation. Therefore, it's a0, a0. So that's going to be the value at c of this difference of these two functions will be 0. So that's written here. Then from here, we want to conclude that differentiable function that starts at 0 and have the derivative around it must be the zero constant function. Of course, the zero constant function satisfies this condition, but that's not really the correct way to argue that this function must be zero function. If you think about the statement I just stated, is actually converse of this statement. We have to eliminate or argue the absolute certainty of the statement that there is no other function that satisfies this condition other than the zero function. So typically in Calculus 1 book, this is done using the mean value theorem. So it's stated here, so I want you to look up the mean value theorem and how this one is done. It's probably definitely is in there somewhere in your calculus book where the applications of a mean value theorem appears. But I'm going to argue the uniqueness in a slightly different way, which will be useful for all the methods that are introduced in differential equations. So what I'm about to do is something you already know. So let me start with what's in here. Think about we have a function. We do some sort of operation. It could be arithmetic or differential or integral, whatever the operation. You can create a new functions. So if you have an equation that involves functions, which is functional equation, if you operate both sides, you will obviously end up at a valid equation. So if the function satisfies certain equation, after you went through operation, that new function we created must satisfy new functional equation. So if you are looking at some unknown fictitious functions here, that function must exist in this solution set as well. That is something you already know. I wanted to point it out because the logic, it is not just some operation or instruction you're asked to do, but you have to understand the logic behind it such that you understand what we mean by the uniqueness of a solution. So if you believe this operation really carries the validity of everything that it's on here and still reside in here, that maybe the uniqueness will make sense. So we start with this assumption, whether their solution exists or not, we assume it exists and see what we can do about it. So we'll come back to the assumption later, but that whole argument depends on this assumption. So we're going to name that function yx, therefore y prime of x is explicitly given function f of x. That's the part of our equation. See what I did over here? This x is an independent variable, so we can obviously rewrite this functional relation with this t variable in it. And then I can do some operation to left-hand side, right-hand side. Right? So understanding the logic through this operation is the key here. So here I'm using the word integral operator. We're doing, here's a functional equation. These two functions involved here, y and f. And we're doing the same thing to the left-hand side and right-hand side to that function. And we create a new function here. Then it's going to be the same because we're doing the same operation, left-hand side, right-hand side, just like adding numbers or raising to the second power. Those are the examples of other operators. So this is called integral operator. This y is t is the variable for the integral. So if you hit it with this one, this creates a new function, right? So integrating from c to x, where x is the main variable, and here we're doing the same thing. So this was one function, and left-hand side we create another function by doing this integral operator through this definite integral. So fundamental theorem of calculus says that if you have an antiderivative of y prime of t, of course that's y of x, y of t, that it's definitely because if the solution exists, then that's before you differentiate it, that's the antiderivative. So yx minus yc, this left-hand side, and this we don't know much about this one. F is just some arbitrary function, so I will leave it this way. But this is well-defined notion. If ft is explicitly given, it's continuous. This exists. by the integrability of continuous function. So we can rewrite as a yx equals to that. So this is given ft, this is completely determined part, and this yc is supposed to be a0. So what this logically says is that if there is a function, that function had no choice. It had to be this particular function. a0 is explicitly given, and this with given ft, this is completely determined. So if it does not have a solution, if it actually there's no solution, the whole thing doesn't make sense. But it has to be this one. So we brought down to this only candidate here. That actually proves the uniqueness of the solution, whether it exists or not. So uniqueness really, if there is a solution and there's only one solution, that's what the uniqueness in mathematics really implies. So they separated the existence to something else, whether it exists or not. It's a separate statement. So this is additional part. Like I said, up to here we prove the uniqueness. And if you want to see actually this is actually a solution or not, in that process of in the fictitious situation, we brought down this candidate. So if you really want to check if that's a solution or not, you have to go through that. So if this is a function, let's actually differentiate that. This whole thing differentiated is a constant. Fundamental theorem calculus again says this has to be just f of x. Therefore, derivative is the function f of x. And y of c, if you plug in c in there, and that's where x goes, to c, the integral is 0, and you're just left with a0. So y of c is a 0 and plus a0. So that checks the second condition, called initial value condition. So this function, we're staring at it here, is actually a solution. And this argument up here says that that's the only solution. So we actually, with this checking, we showed the existence and the uniqueness. So here I'm emphasizing about this, these arrows here. These are the logical and the rigorous implications, that it is not some sort of procedure I'm going through. What you're supposed to understand is that if this is true, this must be true, and that must be true, and so on. That must part. If you understand the must part logically, then the uniqueness should make sense.